How's the royal family? I pray that everyone is doing well. Well, my royal family, I found out this information a couple of days ago, and I'm going to be earnest with y'all. I did not know that there is weather patterns out of space. And so I started researching it, and I said, wow, this is truly amazing and really, really deep. And based on these series of videos that I'm getting ready to present to the royal family, it's getting worse and worse and worse. And it's no surprise to the royal family because the enemy literally was allowed 6 days to rule and reign. And look how it has impacted the entire globe. You know, coronavirus, I always like using that template, how quickly coronavirus went out of control. See, man is vain, and man think that they can conquer everything. And global warming is quite real. I know I did a video a long time ago about the polar cap, and those pictures from those satellites show how the polar cap has melted at an alarming rate, and it's affecting the balance in the universe. And what's actually going on is it's gonna go back to balance. And to get it back to balance, there's a cause and there is an effect on everything in the universe. So my royal family, I'm going to present these videos. I'm glad that I was able to find some videos because some of them words I cannot pronounce whatsoever. I would be jacking it big time. So I will not be reading anything, but this speaks for itself, and I comprehend very well, just like the royal family. So let's first get into this first video. It's only a little over 4 minutes. And the question is, did you know there is weather in space? No, I did not know. Always learning something. Keeps you humble.
So the sun, looking here from the ground, seems very constant and quiet. But actually, when we look at it from space, we can see it's quite turbulent and active. Space weather is activity on the sun and in a near-Earth space that can affect our technological infrastructure and society. The sun is constantly spewing out a stream of particles called the solar wind that goes out into the solar system. And it affects us here near Earth, where we're protected by a magnetic field. The interaction between the solar wind and the magnetic field can cause space weather. The Carrington event is the largest storm we've seen in recorded history when we're looking at space weather. But every solar cycle, which repeats about every 11 years, one estimate estimates that there's a 10% chance of getting a large storm like the Carrington event that could impact us here on Earth. But we see solar storms almost all the time. And these storms have an effect on our technological infrastructure. Solar storms can cause activity in Earth's atmosphere and magnetosphere that can damage electrical power grids that power our communities, interrupt radio and satellite communications, and can cause our GPS navigation to fail. NOAA is working with its international partners to ensure that we have different vantage points where we can observe space weather. Our space weather observing infrastructure from space includes the NOAA Discover satellite and the NASA ACE satellite that are stationed upstream of Earth to give us a first buoy measurement of the solar wind. It also includes the ESA-NASA SOHO satellite and the NASA Stereo satellite that image the sun and also make coronagraph measurements of the outer atmosphere of the sun, the corona, that can tell us when large explosions happen off the sun. We also observe the sun and the Earth's magnetic field from the geostationary location with NOAA's GOES. So the way we use the space weather information from satellites and from the ground is to be able to make forecasts and predictions, just like we do with hurricanes and terrestrial weather. We observe the sun and look for activity and see how it develops and see if it's going to culminate into a large explosion that can affect us here on Earth. NOAA is working with its international partners to expand our observing capability. We're committed to observing along the Sun-Earth line. So we're going to do the imaging of the sun and the upstream buoy measurements of the solar wind along the Sun-Earth axis. The more we understand about the sun, the more we can prepare for it and become, just like we are a weather-ready nation, become a space weather-ready nation. And as we look forward to humans exploring out into the solar system and advancing our space commerce activities, space weather becomes more and more important.
All right, my royal family. So this gives us a nice introduction and a better understanding about weather out of space. But what gets me when I do these types of videos, the enemy's vanity and thinking that they can control some stuff. They can't control none of this. And he said, basically, all we can do is observe. Yeah, that's it and that's all, But they threw that other little thing in there like, we're going to observe this stuff to the point where, if something go down, we'll be able to protect ourselves. You don't play with the sun, and it ain't one sun. I don't know how many suns are out there, but it ain't one sun whatsoever. So when I was really digging and researching, I said, wow, this is a good presentation or a template to start with, because we got many more videos to go into. So let's continue on, my royal family. So on this particular one, I got this video and then I have another short video within. And some of this stuff this guy is talking about on this first video, I have heard some of it, but I didn't really absorb it. But now since, I've researched it, now the things that he is saying, I took it in a different light. I really absorbed this.
Part of this video is sponsored by LastPass. More about LastPass at the end of the show. The butterfly effect is the idea that tiny causes, like a flap of a butterfly's wings in Brazil, can have huge effects, like setting off a tornado in Texas. Now that idea comes straight from the title of a scientific paper published nearly 50 years ago. And perhaps more than any other recent scientific concept, it has captured the public imagination. I mean, on IMDb, there is not one, but 61 different movies, TV episodes, and short films with butterfly effect in the title, not to mention prominent references in movies like Jurassic Park, or in songs, books, and memes. Oh, the memes. In pop culture, the butterfly effect has come to mean that even tiny, seemingly insignificant choices you make can have huge consequences later on in your life. And I think the reason people are so fascinated by the butterfly effect is because it gets at a fundamental question, which is, how well can we predict the future? Now, the goal of this video is to answer that question by examining the science behind the butterfly effect. So if you go back to the late 1600s, after Isaac Newton had come up with his laws of motion and universal gravitation, everything seemed predictable. I mean, we could explain the motions of all the planets and moons, we could predict eclipses and the appearances of comets with pinpoint accuracy centuries in advance. French physicist Pierre-Simon Laplace summed it up in a famous thought experiment. He imagined a super intelligent being, now called Laplace's demon, that knew everything about the current state of the universe, the positions and momenta of all the particles and how they interact. If this intellect were vast enough to submit the data to analysis, he concluded, then the future, just like the past, would be present before its eyes. This is total determinism, the view that the future is already fixed, we just have to wait for it to manifest itself. I think if you've studied a bit of physics, this is the natural viewpoint to come away with. I mean, sure, there's Heisenberg's uncertainty principle from quantum mechanics, but that's on the scale of atoms, pretty insignificant on the scale of people. Virtually all the problems I studied were ones that could be solved analytically, like the motion of planets or falling objects or pendulums. And speaking of pendulums, I want to look at a case of a simple pendulum here to introduce an important representation of dynamical systems, which is phase space. So some people may be familiar with position time or velocity time graphs, but what if we wanted to make a 2D plot that represents every possible state of the pendulum, every possible thing it could do in one graph? Well, on the x-axis, we can plot the angle of the pendulum, and on the y-axis, its velocity. And this is what's called phase space. If the pendulum has friction, it will eventually slow down and stop. And this is shown in phase space by the inward spiral. The pendulum swings slower and less far each time. And it doesn't really matter what the initial conditions are. We know that the final state will be the pendulum at rest, hanging straight down. And from the graph, it looks like the system is attracted to the origin, that one fixed point. So this is called a fixed point attractor. Now, if the pendulum doesn't lose energy, well, it swings back and forth the same way each time. And in phase space, we get a loop. The pendulum is going fastest at the bottom, but the swing is in opposite directions as it goes back and forth. The closed loop tells us that the motion is periodic and predictable. Anytime you see an image like this in phase space, you know that the system regularly repeats. We can swing the pendulum with different amplitudes, but the picture in phase space is very similar, just a different sized loop. Now, an important thing to note is that the curves never cross in phase space, and that's because each point uniquely identifies the complete state of the system, and that state has only one future. So once you've defined the initial state, the entire future is determined. Now, the pendulum can be well understood using Newtonian physics, but Newton himself was aware of problems that did not submit to his equations so easily, particularly the three-body problem. So calculating the motion of the Earth around the sun was simple enough with just those two bodies. But add in one more, say the moon, and it became virtually impossible. Newton told his friend Halley that the theory of the motions of the moon made his head ache and kept him awake so often that he would think of it no more. The problem, as would become clear to Henri Poincaré 200 years later, was that there was no simple solution to the three-body problem. Poincaré had glimpsed what later became known as chaos. Chaos really came into focus in the 1960s when meteorologist Ed Lorenz tried to make a basic computer simulation of the Earth's atmosphere. He had 12 equations and 12 variables, things like temperature, pressure, humidity, and so on. And the computer would print out each time step as a row of 12 numbers, so you could watch how they evolved over time. Now, the breakthrough came when Lorenz wanted to redo a run, but as a shortcut, he entered the numbers from halfway through a previous printout, and then he set the computer calculating. He went off to get some coffee, and when he came back and saw the results, Lorenz was stunned. The new run followed the old one for a short while, but then it diverged. And pretty soon it was describing a totally different state of the atmosphere. I mean, totally different weather. Lorenz's first thought, of course, was that the computer had broken. Maybe a vacuum tube had blown, but none had. The real reason for the difference came down to the fact the printer rounded to 3 decimal places, whereas the computer calculated with 6. So when he entered those initial conditions, the difference of less than 1 part in 1,000 created totally different weather just a short time into the future. Now, Lorenz tried simplifying his equations and then simplifying them some more down to just 3 equations and 3 variables, which represented a toy model of convection, essentially a 2D slice of the atmosphere, heated at the bottom and cooled at the top. But again, he got the same type of behavior. If he changed the numbers just a tiny bit, the results diverged dramatically. Lorenz's system displayed what's become known as sensitive dependence on initial conditions, which is the hallmark of chaos. Now, since Lorenz was working with 3 variables, we can plot the phase space of his system in 3 dimensions. We can pick any point as our initial state and watch how it evolves. Does our point move toward a fixed attractor or a repeating loop? It doesn't seem to. In truth, our system will never revisit the same exact state again. Here, I actually started with 3 closely spaced initial states, and they've been evolving together so far, but now they're starting to diverge. From being arbitrarily close together, they end up on totally different trajectories. This is sensitive dependence on initial conditions in action. Now, I should point out that there is nothing random at all about this system of equations. It's completely deterministic, just like the pendulum. So if you could input exactly the same initial conditions, you would get exactly the same result. The problem is, unlike the pendulum, this system is chaotic. So any difference in initial conditions, no matter how tiny, will be amplified to a totally different final state. It seems like a paradox, but this system is both deterministic and unpredictable. Because in practice, you could never know the initial conditions with perfect accuracy, and I'm talking infinite decimal places. But the result suggests why even today with huge supercomputers, it's so hard to forecast the weather more than a week in advance. In fact, studies have shown that by the 8th day of a long-range forecast, the prediction is less accurate than if you just took the historical average conditions for that day. And knowing about chaos, meteorologists no longer make just a single forecast. Instead, they make ensemble forecasts, varying initial conditions and model parameters to create a set of predictions. Now, far from being the exception to the rule, chaotic systems have been turning up everywhere. The double pendulum, just 2 simple pendulums connected together, is chaotic. Here, 2 double pendulums have been released simultaneously with almost the same initial conditions. But no matter how hard you try, you could never release a double pendulum and make it behave the same way twice. Its motion will forever be unpredictable. You might think that chaos always requires a lot of energy, or irregular motions, but this system of 5 fidget spinners with repelling magnets in each of their arms is chaotic too. At first glance, the system seems to repeat regularly, but if you watch more closely, you'll notice some strange motions. A spinner suddenly flips the other way. Even our solar system is not predictable. A study simulating our solar system for 100 million years into the future found its behavior as a whole to be chaotic, with a characteristic time of about 4 million years. That means within, say, 10 or 15 million years, some planets or moons may have collided or been flung out of the solar system entirely. The very system we think of as the model of order is unpredictable on even modest timescales. So how well can we predict the future? Not very well at all, at least when it comes to chaotic systems. The further into the future you try to predict, the harder it becomes. And past a certain point, predictions are no better than guesses. The same is true when looking into the past of chaotic systems and trying to identify initial causes. I think of it kind of like a fog that sets in the further we try to look into the future or into the past. Chaos puts fundamental limits on what we can know about the future of systems and what we can say about their past. But there is a silver lining. Let's look again at the phase space of Lorenz's equations. If we start with a whole bunch of different initial conditions and watch them evolve, initially the motion is messy. But soon all the points have moved towards or onto an object. The object, coincidentally, looks a bit like a butterfly. It is the attractor. For a large range of initial conditions, the system evolves into a state on this attractor. Now remember, all the paths traced out here never cross, and they never connect to form a loop. If they did, then they would continue on that loop forever, and the behavior would be periodic and predictable. So each path here is actually an infinite curve in a finite space. But how is that possible? Fractals, but that's a story for another video. This particular attractor is called the Lorentz attractor, probably the most famous example of a chaotic attractor, though many others have been found for other systems of equations. Now, if people have heard anything about the butterfly effect, it's usually about how tiny causes make the future unpredictable. But the science behind the butterfly effect also reveals a deep and beautiful structure underlying the dynamics, one that can provide useful insights into the behavior of a system. So you can't predict how any individual state will evolve, but you can say how a collection of states evolves. And at least in the case of Lorentz's equations, they take the shape of a butterfly.
Well,
Hey, this part of the video is sponsored by LastPass.
we're going to listen to the next video. There's a reason for this madness, my royal family. Before we get into the other video, what I gathered from that is they were doing these experiments in a control environment. And at first, they felt like that in that control environment that they could figure out the weather, all kind of different predictions with the moons and the different planets. And over time, it shows you that Yahweh put a whole spin on it, and even in their control environment, that didn't even work. And what gets me is this dude is speaking all intelligent, like they know what's going on, because the biggest concern that Esau have is they want to always be in control. In the space and time that we are in, Yahweh is showing them, you ain't in control of shit. This is my planet. I run it the way I run it. I had told y'all the other night, after we had that eclipse, within that same week, I seen that eclipse, which was south of me. I seen it in that same week north of me. I seen it with my own eyes. And I was like, what's really going on? And you see that they said over a long period of time, they thought they was going to be able to predict weather over a long period of time. And they can't even do that with all they junk out of space and all they fancy equipment and stuff. Because I did one video a long time ago about all that space, all that junk out of space. So this last one is a little over 3 minutes.
Solar flares and coronal mass ejections do not always hit Earth. They happen all over the sun, and depending on where on the sun they occur, determines whether or not they're going to travel towards the Earth.
Some of them could be shot off to the side and just miss us completely. They could go up, they could go left. Some are like curveballs that a pitcher will throw. They could seemingly come straight for us and then miss us completely.
Space weather can have several different effects on the Earth and the near-Earth environment. In space, it can create dangerous radiation in the form of particles, which is detrimental to the health of astronauts. These particles, as well as solar flares, can cause damage to satellites in near-Earth orbit. In addition, electromagnetic disturbances created by geomagnetic storms can affect power transmission on the ground, can also disrupt communication, but space weather has no direct effect on human beings themselves.
Really?
We are protected here on the surface of the Earth from solar flares and coronal mass ejections when they impact the Earth due to the magnetic field of the Earth called the magnetosphere, which deflects the magnetic field and the energetic particles, as well as the atmosphere, which absorbs the higher levels of radiation.
Most of the energy that's associated with a solar flare or a coronal mass ejection doesn't even reach the surface of the Earth. So even the biggest of flares isn't going to affect you here at Earth.
When a large solar eruption occurs, there are generally 3 things that happen. Each of these takes a different amount of time to reach the Earth. The solar flare, because it's light, travels at the speed of light and takes approximately 8 minutes to reach us. The solar energetic particles are traveling extremely fast, close to the speed of light, but not exactly the speed of light, so they take roughly
20 to 30 minutes to reach us. The coronal mass ejection is much slower, and that takes about 1 to 4 days to reach us.
The sun goes through what we call a solar activity cycle, where every 11 years on average, it will go from a very low period of solar activity, meaning sunspots and solar storms, to another period of low activity, and in between it goes through what we call solar maximum. At solar maximum, the sun has a very complicated magnetic field structure, and therefore it creates a lot more sunspots and a lot more solar storms like flares and CMEs. It's very important to be able to forecast solar events because they can affect our technology, our satellites, they can cause power grids to be affected. So as we become more and more technologically advanced, it becomes more important to be able to forecast such events.
Really? Really? That's why I played that first part of that video, because he clearly said that they can't make these predictions, even with all their little fancy ass equipment. And then they sit up there with their vanity and pretty much say, oh, we can't control it. It's a contradiction at the same time, my royal family. All right, as we continue on, I want y'all to listen to this. Oh, wow. And this woman did mention a little bit of this. Will the next space weather season be stormy or fair? Okay. And she speaks of another, this 11-year cycle activity. 11 in the word mean chaos, disorder, and judgment. Y'all following me, my royal family?
Hi, I'm Dennis Overby, the Cosmic Affairs correspondent for the New York Times. Here's my article. The big news about the sun is that there is no big news. We are blessed, astronomers like to say, to be living next to a, quote, boring star. But the inhabitants, if there are any, of the planets orbiting the neighboring star Proxima Centauri, only 4.2 light years away, are less fortunate. In April, astronomers announced that a massive flare had erupted from its surface in 2015. For 7 seconds, as a battery of telescopes on Earth and in space watched, the little star had increased its output of ultraviolet radiation 14,000-fold in one of the most violent such flares ever seen in our galaxy. This was more than serious sunburn territory. Quote, "A human being on this planet would have a bad time," said Meredith McGregor, an astronomy professor at the University of Colorado who led the worldwide observing effort. Space weather on this scale could sterilize potentially habitable planets and could augur bad news for the search for life beyond this solar system. Even mild space weather can be disruptive to creatures already evolved and settled. Sunspots and solar storms, which wax and wane in an 11-year cycle, spray energy that can endanger spacecraft, astronauts, and communication systems. A new cycle of storms will begin any day now, and astrophysicists are divided on how active or threatening it will be. The sun may be about to set records for sunspot numbers in violent storms, or it may be sliding into a decline like the Maunder minimum from 1645 to 1715, when hardly any sunspots appeared, a period that became known in Europe as the Little Ice Age. We live in the atmosphere of a star, as Scott McIntosh, a solar physicist at the National Center for Atmospheric Research in Boulder, Colorado, often says. Quote, "As a civilization, we take our star for granted. Here, 93 million miles from the nearest star, the one we call our sun, we exist and mostly thrive on the edge of almost incomprehensible violence and complexity. The sun is a medium-sized star, a ball of blazing hot ionized gas 1 million miles in diameter. Its large inside rotates faster than its outside, and the outer layers rotate faster at the equator than at the poles. The result is a snarled nest of magnetic fields, which manifest as sunspots and worse when they break the surface. Every second, thermonuclear reactions in the center of the sun burn 600 million tons of hydrogen into 596 million tons of helium. The missing 4 million tons, turned into pure energy, constitute the mortgage payment for all the life on Earth, and perhaps elsewhere in the solar system. As the energy emerges from the sun, it rises through successively cooler and less dense layers of gas, and finally, 100,000 years later, from the photosphere or surface, where the temperature is a mere 5,700 Kelvin, or 9,800 degrees Fahrenheit. The sun is amazingly consistent in making these mortgage payments. A few years ago, an experiment in Italy confirmed that our star does not seem to have changed its energy output in at least the last 100,000 years, the time it takes that energy to migrate from the sun's core. The researchers were able to calculate how much energy the sun produces in real time by measuring subatomic particles called neutrinos that are produced by nuclear reactions inside the sun, escape in seconds, and reach Earth in just 8 minutes. This energy, they found, matched the output that was generated 100,000 years ago and is only now detectable. The action doesn't stop at the sun's surface. That friendly yellow photosphere boils like oatmeal and is pocked with dark magnetic storms, the infamous sunspots, that crackle, whirl, and lash space with showers of electrical particles and radiation. The corona, composed of thin, superhot streamers of electrified gas, invisible only during solar eclipses, extends millions of miles from the glowing surface. Things sometimes go wrong, although so far on a scale far below the outbursts seen on Proxima Centauri. As the magnetic fields generated by all that swirling electrified gas emerge from the sun's surface, they become twisted and tangled. Eventually they snap and reconnect in loops, releasing enormous amounts of radiation and charged particles, an explosive solar flare that can be more powerful than millions of hydrogen bombs. Sometimes these flares blow whole chunks of the sun's outer layers into space in events called coronal mass ejections. The mother of all known solar storms thus far occurred on September 1st, 1859, when a blob of sun slammed into Earth. Sparks flew from telegraph systems in Europe and North America, causing fires. The auroras that night stretched as far south as Hawaii and Cuba, and were so bright that people could read their newspapers by their light. In 2012, another coronal mass ejection barely missed the Earth. An earlier study by the National Academy of Sciences concluded that a direct hit by such a storm could cause some $2 trillion in damage, shutting down the power grid and rendering satellites at least temporarily blind. Forget about trying to use the internet or your local ATM. Many people wouldn't even be able to flush their toilets without the electricity to run water pumps, the report noted. Quote, "I think as a civilization we become screwed," Dr. McIntosh said. Such storms are more likely to occur during the high points of the sun's mysterious 11-year cycle of sunspot activity. Lately, the sunspot cycles have been getting weaker. During the last cycle, 101 spots were observed on the sun in 2014, the year of peak activity. That was well below the historical average of 160 to 240. Last year, a committee of scientists from NASA and the National Oceanic and Atmospheric Administration forecast that the coming cycle would be similarly anemic, with a peak in 2025 of about 115 sunspots. But Dr. McIntosh and his colleagues have produced a radically different forecast of more than 200 sunspots at its peak. The 11-year sunspot cycle, they say, based on an analysis of 140 years of solar measurements, belies a more fundamental 22-year Hale cycle, named after its discoverer, George Ellery Hale. During that period, the sun's magnetic field reverses its polarity, then switches back. Each cycle ends or begins when two bands of magnetism migrating from opposite high latitudes of the sun meet at the equator and annihilate each other. On average, each phase of the cycle takes 11 years, but it can vary. Dr. McIntosh and his team found that the longer a cycle went on, the weaker the next cycle would be, and vice versa. The current cycle, the 24th since record keeping started, shows every sign of ending after a little more than 10 years, shorter than average, which means the next cycle should be strong. Quote, Sunspot cycle 25 could have a magnitude that rivals the top few since records began, Dr. McIntosh said in late April. On Thursday, he and his team were still waiting for, quote, ignition to begin. Quote, it is very, very close, he wrote in an email. Quote, we are watching very closely. At stake, besides the health of our planetary infrastructure, is the pride that astronomers take in feeling that they understand the complicated and violent processes going on behind the sun's relatively calm face. Quote, I think the problem with the sun is that we're too close to it, and so there's too much data about the sun, Dr. McIntosh said. He called it a breaker of models. Quote, your models are going to fail eventually. It's part of the reason why it's so hard to forecast the weather, right? Because our observations are so detailed, but it's hard to get it absolutely right. Tony Phillips, an astronomer who runs the website spaceweather.com, agreed in an email. Quote, in my experience, when people really understand something, they can explain it simply, he said. It is striking to me that almost no one in the solar cycle prediction business can explain their favorite dynamo model in a way that lay people can get it. The situation reminded him of the proverbial blind men who tried to produce a theory of elephants, with one of them focused solely on feeling the elephant's trunk. Scott and Bob are standing off to the side, shouting, quote, hey, you guys are ignoring most of the elephant, he said. Quote, in other words, there's more to the solar cycle than is commonly assumed by conventional models. And so, according to Scott, they are doomed to get the big picture wrong. Jay Pasakoff, an astronomer at Williams College who has spent his life observing the corona during solar eclipses, said he did not put much store in such forecasts. In an email, he recounted a meeting during the last cycle that had, quote, an amusing set of talks. The conversation as he recalled it went, quote, the next cycle will be stronger than average. The next cycle will be weaker than average. The next cycle will be either stronger than average or weaker than average. The next cycle will be neither stronger than average nor weaker than average. He added, quote, so my plan is to wait and see. Potential hazards aside, understanding how the sunspot cycle really works is crucial, quote, from a purely human standpoint if you want to understand stars, Dr. McIntosh said. Quote, and if you think about it, Earth's magnetic field is largely why we probably have life on Earth. Mars, he pointed out, doesn't have much of an atmosphere or a magnetic field. Quote, if your planet doesn't have a magnetic field, you can have all the atmosphere you want, he said, but your friendly local neighborhood star could whisk it away in a heartbeat. Indeed, astrophysicists suspect that such a fate befell Mars, which was once warmer and wetter than it is now. Proxima Centauri, a small star known as an M-dwarf, harbors at least 2 exoplanets, one of which is Earth-size, and close enough to the star to be habitable if it weren't bathed in radiation. Dr. McGregor offered one glimmer of hope for life in such neighborhoods. Quote, recent work has shown that ultraviolet light might be very important for catalyzing life, turning complex molecules into amino acids, and ultimately into single-celled organisms, she said. Since M-dwarfs are so small and cold, they don't actually produce that much UV radiation, except when they flare. Perhaps there is a sweet spot where a star flares enough to spark life, but not so much that it immediately destroys it.
Well, my royal family, I meant to say that article, where's the date at on that? Okay, that was May 28th, 2021. That clearly spoke that there's a lot of activity in the universe. I got one more video, but it's short. And what I was thinking about was when the first shutdown happened and throughout the globe, the water was getting cleaner, the air was getting cleaner. I remember something along about the Himalaya mountains. Some people had never even seen them. So man itself on Earth with all this technology, people driving their cars and all of that, it has a cause and effect. So, it's melting the polar cap. We got all these crazy extreme weather patterns and all of that. And the universe is in a process of getting thyself back in order at the end of the day. So here's this last quick short video, my royal family. And this article came out June 7th. Highest in more than 4 million years, Earth carbon dioxide levels soar to record high despite pandemic. This stuff is real. Yahweh is not playing.
A group of experts from geology to physics say that climate change should be treated like World War III in a message published at theconversation.com. They listed their top 4 ways to start fixing the climate right now. First, trees have enormous potential to cool down the atmosphere by fueling clouds and rain. The Earth has plenty of room for new forests, adding up to an area bigger than Brazil, and Australia is a good place to start. Since fossil fuels start out as other forms of carbon, humans could transform carbon dioxide into rock using the same processes found in nature, from limestone to seashells. Surfaces like asphalt and dark rooftops are trapping more heat than they have to. By using more reflective materials, we could send sunlight right back into space. Finally, some changes to transportation would make a huge difference. A speed limit for cargo ships would cut back on carbon emissions, and countries should provide tax breaks and other privileges for electric cars.
Really? Well, this is what I have to say, Esau. You are too damn late with all of that. There ain't nothing you can do. You done tore up this damn planet, and now you want to do some hurry up, quick shit. You didn't respect the Earth. And then you think you can go out of space and you think you're going to live on another planet because you see activity over there. There's water over there. It's not going to happen whatsoever, my royal family. We all know it. But these videos I have presented to y'all shows the enemy's vanity. They're quite vain, and they know they are doomed because they can't help themselves. They're always digging into stuff. Do you know, my royal family? They're looking for their origin, and they're also looking for the fountain of youth as well. They're not going to find none of that. You don't have no damn origin at all. I love that saying I had picked up on years ago. The deeper you dig, the blacker the planet. So this was quite enlightening to me because I was not aware that there was weather, but it makes all sense. Outer space. Like I said, I had did a video a few years ago about all the space junk, which is disgusting. They didn't put all them satellites and all that crap out there, and then that stuff, phase out over time, and they don't, they have went out there and cleaned it a little bit, but it is enormous. It is enormous. And maybe I should do a video on that. Sometimes it's nice to redo videos. But I just wanted to present this to the royal family. I know some of y'all out there know it, but it was enlightening and new to me, and I just felt the need to present it to the royal family. So as always, my royal family, render your voice with your beautiful divine words. And as always, I thank you for your love. I thank you for your support. And with that said, Ashe.